In this video, I want to tell you about homeomorphisms between spaces. So homeomorphisms are maps. The idea is that these are maps fx to y between two metric spaces that preserve everything. So that means that they preserve conversion sequences, they preserve compactness, they preserve connectivity, and every other notion that we define in this class. And to do that, by looking at these different statements and theorems that we have, in a sense, what you have to have, you have to way of going from x to y and from going backwards. A way of thinking about this is that if there is such a homeomorphism, that means that these spaces are kind of the same. So when is x the same in some sense as y from the perspectives of this class? So the kind of picture to have is that if you take this red curve, this is the same as a circle. I mean, we understand that one is just a bent copy of the other one. They have different distance functions. Say the distance between these two is like that, and if you could, the corresponding points here would be like that. The distances won't be exactly the same in these spaces, but in a lot of ways, things are the same. So there is a notion of open intervals, say, in both cases, and these match to each other. So there is a map that takes one to the other and goes both ways, f and its inverse, and it preserves every notion from this class. So topologically, or as metric spaces, these are essentially the same. So what is this notion? This notion is called homeomorphism, and it's a concept that involves a map from x to y, and it requires two things. One is that you have a bijection, that means one-to-one and onto. This is an assumption so that everything in y corresponds to something in x, but corresponds to only one thing in x. This way, the sets are the same, essentially, up to this reparameterization. And you could think f as being the reparameterization map. But then we require that more than that, we require that this map is continuous. That is, that f is continuous and its inverse is continuous. It could fit. It's not enough that f is continuous. This property could fail if the inverse is not continuous. So I will say the theorem, which I will not prove. It's a good exercise to prove that if you have a homeomorphism, and sometimes this is abbreviated homeo, then a subset V of x is open if and only if its image is open. Another set is closed, again, as of x, if and only if its image is closed. A sequence converges if and only if its image sequence converges. So yn is equal to f of x, and y by continuity would have to equal f of x. And a set is compact if and only if the image set is compact. And a set is connected if and only if its image set is connected. So this means that every notion that we've defined so far, 1 through 5, is preserved by such a function. So in terms of statements of this class, or in the language of this class, these do not differ at all. So you can transfer statements from x to statements of y, and proving things are equivalent. And the idea is that you play with these inverse functions, and you play with the fact that f is equal to inverse of f of a, and then you also use sometimes the fact that the inverse of the inverse function is equal to f. It's worthwhile to define that and verify. So some examples. If you have the open interval 0 to infinity, this is homeomorphic or homeo to R by sending x to 1 over x minus x. Now, this formula might not make much sense, but if you look at the graph of this, it becomes more intuitive. Well, it has a vertical asymptote at 0, and it goes to negative infinity monotonically because both of these are decreasing. So this is one-to-one and onto, as can be verified by inverse function theory, and it's continuous. And a theorem from 131a says that if you have a monotone function, its inverse is continuous. It could also be derived from one of the statements in this class. Now, another extreme thing is that the open interval 0, 1 is homeomorphic to all of R. And again, you can come up with a function that sends x to 1 over x minus plus x minus 1. And the idea here is that you have 0 and 1 here, and you have the vertical asymptotes at 1, so that's where you go off to infinity, and then you go off to negative infinity. You could also use things like tangent of x, but I wanted to give algebraic things that are easier to work with. So in this case, functions are continuous on both directions. And it also shows that a subset, even a very small subset of the whole thing, can be essentially the same as the whole space. So for some things, this really is a powerful idea. But another thing that it shows, the second example especially, is that certain properties are not preserved. I mean, this is unbounded, the whole real line, and this is bounded. Yet you can get a correspondence between these examples which is one-to-one, onto, and which is continuous in both ways. So in some senses they are the same, but there are senses in which they're not. So boundedness is not preserved, and also completeness is not preserved. So there are some notions of this class that are more dependent on the metric than just on the sort of topology or this notion of homeomorphism. But this notion is already enough to distinguish certain spaces, to say that they're really different. So we can, for example, say that the rational numbers q and all of the real numbers, they're different in that they're not homeomorphic to each other. The closed interval 0, 1 is not homeomorphic to the open interval 0, 1. And the closed interval 0, 1 is not homeomorphic to S1. And S1 here is defined as all the points in the plane, such that x squared, y squared is equal to 1, with its restricted topology. So what does it look like? It's the unit circle in the plane. Unit circle with nothing inside. Now, the idea with proving these facts is that you observe some difference. So how to prove is that you observe a difference. And it has to be one of the differences that we mentioned in this theorem. So either you find an open set whose image is not open, closed sets whose image is not closed, or you find convergent sequences that fail to converge on the other side, or a compact set whose image can't be compact, or a connected set whose image can't be connected, or vice versa. So these properties are preserved by homeomorphism, so they can be used to distinguish spaces. So in this case, Q is disconnected, but R is not connected. So that's a simple example. Why is Q not connected? Why is Q disconnected? Well, Q is equal to the union of two sets that are open. So one is minus infinity to square root 2 intersected with Q. This is my U. And the other one is square root 2 up to infinity intersected with Q. Both of these are relatively open in Q. So I'm thinking of Q as being the whole space here. It doesn't matter actually for this problem. You could just forget about this. It's still true without the intersection if I put a subset there, and then I would get the subset definition, and this would be equivalent. So Q is disconnected. Because this gives me a cover UV, open, disjoint, non-empty. Okay, but R we showed is connected. And connectivity is preserved by homeo, so they cannot be homomorphic. Okay. So that shows that there cannot be a bijective continuous map from D-space. Now, let's do the same for the similar for the closed interval. Now, there are different proofs that you could do, but a simple one involves compactness instead of connectivity. You have the closed interval 0, 1 and the open interval 0, 1. Well, you want a difference. One difference is this is compact. The open interval 0, 1 is not compact. I'm talking with the normal metrics on them. But if that's the whole space, if they're bijective, then the image of the closed interval 0, 1 would be 0, 1. But this is compact, and open interval 0, 1 is not compact. So can't be homer, as compactness should be preserved. So you can think of this as a contradiction argument if you start from the homomorphism. Now the third thing is the interval is not homomorphic to the circle. Now this should be, you should think the picture also a little bit. So the interval is just like we imagine an interval, it's a line segment, and the circle, S1, is a circle. Now these two look different. They have some differences, and one of the differences is, we want to make it more precise and really identify a difference that prevents these from being the same. And one is that if you remove a point from S1, then it's still connected. Why is that? Because you can still connect by a path. But if you remove some points from the interval, say the middle point, then you disconnect the space. So the interval can be disconnected by a point, removal of a point, but the circle cannot. So this is a difference between these spaces that prevents there from being a homomorphism. And this idea actually can be used much more generally and in a more complex setting to differentiate between spaces. But so let's suppose there was a homomorphisms, then, well, f of a half would be mapped to some point P. And this part can be expressed differently. So if we define A as 0, 1, take away the point a half, this is disconnected. And f of A is equal to S1, take away a point, is connected. Now, why are these the case? Well, we have to be careful here. So the interval removed the center. That's disconnected because you can cover it by two sets, all the points up to a half and all the points bigger than a half. That gives you a covering by two disjoint, non-empty open sets U and B, which contradicts connectivity, so shows it's disconnected. S1, on the other hand, if you remove a point, is still connected because it is path connected. I mean, this requires a careful argument, but it is path connected because you have a curve that goes the other way around. I mean, that would be technical to write. So this is connected. The pre-image is not connected, but connected maps should preserve so is homo, so preserves connectivity. But we define this set X prime, which is disconnected, images Y prime, which is connected, and this is a contradiction because F preserves connectivity of subsets. End of proof. So the lesson to take out of this proof is that if you want to show that spaces are different, you can focus on some of the properties that we have defined in this class, namely connectivity, compactness, openness, closeness, and convergence, and you can try to find a difference that is irreconcilable between these spaces. Now, most often, they're in these simple cases, you use connectivity and compactness. And often there are many ways. You could also use the fact that Q is not compact to include that Q and R are not homeomorphic.